everyone, today I'm going to present my research with the title is The Airborne Particles in the Fiber Matrix, a Stochastic Approach. My talk includes 5 sections. The first one, introduction. The second one is the random motion of airborne particles. Then SDE solvers. The next one is airborne particles in mass filter matrix. And the last one is the conclusion. Let's start with the introduction. The airborne particles are extremely small, under 10 micrometers, and can be suspended in the air from 30 minutes to an hour. The motion of a particle is the result of random and rapid collisions due to the density fluctuation in the fluid. According to the new research, the smallest size of a respiratory particle that can carry SARS-CoV-2 is around 4.7 micrometers. Normally, the ODEs cannot satisfy the small-scale simulation because the random elements are ignored. In this study, we will present a stochastic approach by incorporating the Langevin equation into the flow field to simulate the movements of the airborne particles and see how it interacts with the fiber matrix to improve the air filtration performance. We consider a particle immersed in the fluid. According to the Newton's second law, the force acting on a particle is equal to its mass times the acceleration. The force will include a friction force and a random force. NWT is a window process. And this is the general form of a SDE, where F and G are two real functions. For most SDEs, it's difficult to find an exact solution. The Euler and the Milstein methods are two simple and successful approaches for approximating solution in SDE. This is the general form of the Euler method. Then we will apply this method to the Black-Scholes equations. These equations have the exact solution. And this figure shows the exact solution and the Euler approximation. The convergence rate is 0.5. It's possible to raise the strong order of Euler method to 1 by adding a correction to the stochastic increment. This correction comes from the traditional Taylor expansion. We also apply the Milstein method to the Black-Scholes equation. And we have the exact solution and the approximated solution. The Milstein method has a degree of convergence is 1. The most dominant filter mechanism are interception, inertial induction, and diffusion. The interception occurs when a particle follows the gas streamline. The interception of particles is common for large particles. And the next one is the inertial induction. The inertial induction occurs when a particle is so large that it is unable to quickly adjust to the changes in the streamline direction. The particles, due to its inertial induction, it will continue along its original way, then hit the filter fiber. The next mechanism is the diffusion. The small particles with the diameters in the range of 0.1 micrometer or below will tend to make the random motions due to their interaction with the gas molecules. diffusion towards porous media occurs for a very small particles, such as viruses. For the simulation of the airborne particles, we have the Langevin equation. The Langevin equation is used for the motion of the airborne particles in the gas streamline, in which m is the mass of the particle, T is the temperature, Kb is the Boltzmann constant, ρ is the air density, and mu is the air viscosity. We consider a particle with a diameter of 0.5 micrometer. And this figure shows the two-dimensional simulation of an airborne particle in the fluid flow with the initial position is 0, 2. Similar, we have a different initial position A, 0, 0. In this case, we consider the air velocity is Vx and Vy. Vx 0.2 and Vy is 0.3 meter per second. Similarly, we have the 3D simulation. The air velocity is Vx, Vy, and Vz. And the particle comes from different initial position. And this is the matrix of filter fibers. We consider the particles originating from different random locations A, B, and C. The next one is the mean square displacement. After a time delta t, the particle has undergone a displacement delta x, and this is the formula for the mean square displacement. This is the starting point, and this is the ending point. In the figure A, as we can see a large particle due to the impaction, it will not be able to respond to the rapid fluctuation, and then will move on a nearly straight line. If the average space between the surfaces, the face mask and the face skin, is much larger than the surface roughness, the particle may pass without hitting the wall. In this case, if the Brownian motion is big enough, the particle may hit into the wall even if the average space is large. In the figure B, if the average space is smaller, the surface roughness, then the particle is likely to hit into the solid wall. In this formula, we suppose the distance between two surfaces is 0.7 micrometer. Then we will have the estimated radius particle is the 10 power minus 11 meter. This is the difference in the phase mass filter, where the open channels may on the average have a diameter of 1 micrometer. This could enhance the diameter of a particle, which will make the Brownian motion important for particles smaller than 0.1 micrometer. If we consider the bore size is 1 micrometer, then we will have the estimated diameter is 10 power minus 8 meter. This is the size of the viruses. The filter efficiency is defined as the ratio of the upstream particle concentration compared to the downstream concentration that has passed. Then this formula is to calculate the filter efficiency. This is the downstream concentration, and UC is the upstream concentration. According to SCONA 2022, a 600 TPI cotton pad can have an average filter efficiency of 79%, with the particles ranging from 0.01 to 0.3 micrometer. The last section is the conclusion and the future work. In this work, by solving the stochastic differential equations, we were able to simulate the random motion of the airborne particles and see how they interact with the filter fiber matrix. The movement of the particles are computed in 2 dimensions as well as in 3 dimensions. In the future work, we also conduct the PIV, the particle image velocimetry, as a particle counting by adding a tracer, illuminating the fluid with a laser sheet, then capturing the images of the tracer particle movement. By counting the number of particles in the images, we could estimate the concentration of the particles in the fluid. Then we will do this test with different kinds of masks. For example, the cloth mask, the blue surgical mask, N95 mask, and nasal filter. Then we will compare with the simulation to examine how the airborne particles interact with the fiber matrices of the face masks, leading to improve the filtration performance and better mask designs. Here are our references. Thank you for listening.